Hello all. Welcome again to this session on the dimensional reduction techniques. So in the first two sessions, you'd seen um, a detailed introduction on the dimensional reduction by Charul and Abhirup. I'm Ravi Shankar. I'm an applied scientist in the geospatial team. So in the third part, what we're going to do is we'll look at the dimensionality reduction in the age of LLMs and the generative AI. So in the first two sessions, you might have seen techniques like the principal component analysis and how it is being calculated using by borrowing topics from linear algebra like the SVD, the singular value decomposition, and other things. And also you might have seen in great detail the concepts like the curse of dimensionality. So in this particular section, I'll take you into how these dimensional reduction techniques are currently working in the age of the generative AI, which is of greater interest. Mhm. So I split this particular session into four subparts. In the first part, we'll be seeing autoencoders and slowly venture into the most advanced techniques like the variational autoencoders. In the second part, I'll be talking about the other set of models like the latent diffusion models, and then followed by the low rank methods in transformers, where the fine tuning of the state of the art LLMs in a reduced dimension or a smaller subspace, the parameter space. Followed by in the fourth part, we'll look at the embedding models like the recent Matryoshka representations, where you can learn you can do you can do the dimensional detection in hierarchical way. Yes, let's just go ahead. Yeah. So in the part one, we'll talk about the autoencoders and the variational and slowly move towards the variational autoencoders. So this part, the first part builds on the foundation for the whole talk actually. So we'll start with a plain autoencoder and see why a bottleneck forces the dimensionality reduction, and then we subsequently look at the two classical variants of the autoencoders, mostly a denoising autoencoder and a sparse autoencoder. So after that, we will motivate the variational autoencoder and then finish with the VQVAE, also called as the vector quantized variational autoencoder, where a discrete latent model behind many of the state-of-the-art image generation techniques like DALI. So at a high level, what in the first step, what we see is we try to compress the data into a latent space and control what the space look like. So, so what you see here in this particular image is an autoencoder where the simplistic idea is one of the simplistic idea in representation learning. So what the autoencoder tries to learn is it tries to learn an identity function where a neural network is trying just to copy its input to the output. You can see here where an input image 4 is just copied or try to reconstruct, or we try to reconstruct the same image 4. So although this sounds very trivial, why we want to train a neural network to output what we already gave it. So the trick is in the bottleneck in the middle that you see here. So a layer with far fewer dimensions than the input. If you look at here, you have a 24 by 24 pixel image, but the latent representation C could be really small. So we're essentially trying to learn the network in such a way that to reproduce the input image through this narrow channel, the network just can't just pass through the data. It has to discover a compact mode that essentially captures all the useful information in this particular input. So the left hand, that is this encoder. This part compresses the input X down to that small c. And then the right half that you see here, the decoder then tries to reconstruct this x hat, or reconstruct this x prime from this the code vector. So concretely, if you take this 28 by 28 image, that's a 784 dimensional representation, and it force through a trivial a 20-dimensional bottleneck, the decoder has to rebuild all these 784 pixels from just this 20. If it does that well, these 20 numbers are genuinely useful compressed representation. So you can just throw away the decoder and instead of storing this entire 20 feet by 24 image, you can just store this the 20 dimensional representation or whatever a hyperparameter that you currently have. So that's dimensional redirection learned from data rather than hand designed. So how about this bottleneck future? That is why this bottleneck really matters much. So in the middle layer that you saw in the previous slide uh, was very small. So if it was wide as the input, the network could learn the identity function, just copy values straight through and learn nothing useful actually. So the bottleneck kind of removes that option, right? I mean, so with the latent dimension much smaller than the actual original input, so the network is kind of forced to learn a much forced to learn only the that is actually useful, and what it throws away is noise and redundancy, while it keeps the information structure. So you can think of each layer as as it progressively stripping less information type dimensions. So the deeper layers see more and more abstract features. Like if you're learning images, the initial layers will be just learning the edges, and the higher layers will be learning much abstract features. And the key thing that makes an autoencoder more powerful than the classical methods is the non-linearity that is present. That's a supervisor. It's what lets the autoencoder bend and curve to fit data that a linear model can't. So how do we learn these autoencoders? So let's make the training concrete with the simplistic example possible. Let's start with the linear autoencoder. So the encoder is just matrix multiplication. You take this input x and then multiply by v times x, which projects this into some a lower dimensional, a k-dimensional plane. Um, now that's dimensionality reduction step. The decoder is just another matrix U that maps this small k-dimensional back to this d-dimensional reconstruction. So the whole model is the x hat equals to uxv, which is a purely linear function. So training means that you wanted to learn the weights of this model, which is this u and v, so that the reconstruction here is as close as possible to the input. And and how do we measure that? As we formulate the loss as some squared error kind of thing, which is a norm of x minus x cat. So we minimize that loss to learn this u and v. Now, two limitations to flag. I mean, because they set up the rest of the talk actually. So first, this model is non-generative. It can compress to some very small dimension and rebuild existing data. But if you feed it to some random code, let's say you randomly sample some k-dimensional vector here and try to reconstruct, you won't get any meaningful new sample. The second is, I mean, how do you know what is the sample what is the dimension of this k units? Let's say when you take an MNIST, I mean, is a hidden dimension 20, 40, which is a hyperparameter, which we don't know. So both of these questions are exactly what a kind of a variational autoencoder can potentially answer. Right. So in this is an interactive slide. Let me show you this live actually. So what you see is on the left hand is the original image, which is at a full rank, and on the right is the reconstructed image. So there's a small slider that I provided is the latent dimension k. So a linear encoder with just a squared error losses mathematically identical keeping the top k components of the SVT actually. This is a PCA, so it's a faithful picture of what the bottleneck is. So as we move the slider from k is equal to 1 to the higher dimensions, right? You can closely see that at k is equal to 1. So it means essentially you just map this entire original image into one single dimension, and then when you try to reconstruct that, what you see is, I mean, just like a coarse blob, right? And the reconstruction rate is really high. So the reconstruction is extremely high, some 0.278. So as you drag up slowly, as I add more and more components to this. I mean, you can slowly see that the reconstruction error is slowly going down, and you slowly start seeing the input image coming up. In fact, as the hidden representation increases, at some point of time, let's say at k is equal to 16 out of 28 dimensions, the reconstruction error is actually 0. So the key takeaway is information is not spread across evenly across all the dimensions. The first few components carry most of the information. Let's say in this particular case, even with k is equal to 5, you were able to do a fairly reasonable reconstruction of the input image. So that's the whole the bottleneck trade-off, and it's the same principle that will let us compress embeddings and also run diffusion in the later latent space. Now, uh, so as we mentioned, we'll see two other variants in this autoencoder, with the first variant being the denoising autoencoder. So a plain autoencoder has a very subtle risk. If you see, with enough capacity, it can actually basically memorize actually. So, or essentially it means, we are at the risk of doing an overfitting. So the denoising autoencoder actually fixes this problem with a simple change. So instead of feeding the network with the clean image, what we do is we deliberately corrupt the data. What I mean, so you would have small noise, or you mask out few samples, and then you ask the network to reconstruct the original image with this noisy input. So earlier the input for the autoencoder used to be this, but you put up with some noise and you add noise to this. So for this noisy input, the network is learned in such a way that it tries to reconstruct the original image. Right. So to fill in what was listed, the model has to learn the relationship between the input dimensions. It has to understand that these pixels tend to go to there so that it can infer the misevents, and that actually produces a much more robust representation. The loss is actually the same. I mean, we just can just use a squared error and just measure a clean target and reconstruct from the corrupted output. So let's see the denoising in action actually. So it has three panels. I mean, you see a very clean digit on the left, a slightly noisy version in the middle, and this is what the network receives, and the denoised output on the right. So as the slider controls, and the slider that I have controls the amount of noise that I add. So as I crank up the noise, right? I mean, the middle panel turns out to be, kind of static. As I add more and more noise, I mean, which is the input that I'm giving to the model, the more and more noise, I mean, it's just some static image kind of thing, right? Uh, so the middle panel turns out, but what's the right panel? I mean, it still records a clear digit. Let's look at this. I mean, so at here I have some noise level 10 added, but I mean but still, if you look at the input versus the denoised, I mean, it is still able to learn or essentially able to recover much of the input image. And also, let's look at the two error number. The noisy error climbs much faster actually, but the denoised error stays much low. So the intuition is the signal, that is this actual digit lives in a few stronger components, a lower dimensional subspace, whereas the noise on the other hand is a spread thinly across all the components. So when the decoder keeps only the top components and then drops the rest, it also keeps almost all of the signal and throws away the most of the noise. That's the core idea behind this denoising, and it's the same LoRack principle that we just saw in the bottleneck. So the other variant that we have is the sparse autoencoder, where takes a slightly different route to get a good representation actually. So instead of forcing a narrow bottleneck, a sparse autoencoder lets the hidden layer, to be wide, but actually adds a sparsity constraint, where only a small number of neurons are actually allowed to fire for any given input. Each neuron should stay quiet almost all the time. We formalize that with a target sparsity. Each neuron should be active only, let's say, 5% of the time. And we push each neuron's average activation toward that particular target. So there's a penalty term that we use in the loss function, where the penalty is a KL divergence between the desired activation rate and the actual one added to the reconstruction load. So you get robustness without a hot bottleneck. And you can see that, I mean, if you plot the KL loss between the row and row hat across many other row hat, you can see that at row is equal to point. If you're trying to minimize the loss at row is equal to 0.25, you essentially end up having the lowest KL divergence between a Bernoulli with row 0.25. So researchers train them on models internal activation to actually break them into sparse monosemantic features. So an individual direction that corresponds to, and these are this individual direction that correspond to these human interpretable concepts. Because that's how they're actually related to the LLM interpretability concept also. So let's have a quick check, a very small quiz on this autoencoder. If a standard autoencoder uses only a linear activations and an MSE loss, how does it it's learned subspace related to the PCA? We can take a pause here and try to answer this. And the answer is it spans the same subspace as a top K principal components. Now, why we further want to go ahead with the other model, that is this VA, the which is the variational autoencoder. The motivation for the variational autoencoder start here. Now let's pivot to the generation. We have been seeing the reconstruction. Given an input image, we try to reconstruct everything. So everything so far reconstructs really well, but can we generate the new data is a fundamental question that we wanted to answer. So with a plain autoencoder that we said, a beaten autoencoder, sparse autoencoder, the denoising autoencoder, we typically can know, and it's worth understanding why actually. So the encoder was never ever trying to encode and decode existing was only trying to decode from these existing points. So what I mean by that, so when you pass an input to the encoder, it gives you a static Let's say this is the cat image that you currently have, and the decoder has never seen any perturbed variation of this particular latent representation to generate a different kind of cat. So that's one foundational limitation. So now its latent space has no structure imposed on it. So that's the reason the model tend to uh, uh, scatter training examples into this isolated kind of pockets with there's a large empty gaps between them. Let's say if it is a cat's image and this is a chair's image, if you want to generate something like a cat sitting on a chair, I mean, if you randomly sample, so if you interpolate between this point and this point and start here and just try and give it to the decoder of let's say a sparse decoder or a denoising decoder, you'll not get a cat image along with a chair, because the model has never seen a latent representation from somewhere here during this training. So if you sample a random point, what you can do is you can sample a random point in that space and decode it in the hope of generating something. You cannot do that. So what we want is that the latent space to be continuous actually. Right, I mean, it has seen some, the decoder has seen some points over here. So how do you do that? Instead of mapping it to a very static kind of point, you map it to a distribution, right? What we want is a latent space that is continuous, where similar input land near each other and compete, and then every region tries to decode try to decode something valid. So the variational autoencoder actually achieves both by encoding each input as a distribution instead of a single point, and regularizing those distributions. So this is the variational autoencoder where we encode as a distribution, not as a data point. So here is the key mechanism. So instead of mapping an input to one vector, the VAE encoder outputs two vectors actually, a mean vector and a variance vector. So together they define a Gaussian, something like a kind of little cloud of probability in the latent space that we saw in the earlier space. A Q of Z given X actually. So to get a code, what we do is we sample a point Z from that cloud and hand it over the decoder because we saw the nearby inputs produce overlapping clouds. The space between becomes smooth and continuous. But there's again a problem. I mean, the problem is when you sample something, you cannot backpropagate through a random draw, right? So that's why these people have come up with something called as a reparameterization trick, which is shown here, where instead of sampling C directly, what we sample is we sample a standard normal epsilon, and then compute z equal to mu plus sigma times epsilon. So now all the randomness actually sits in the epsilon, which has no learnable parameters, and mu and sigma are on a clean differentiable path. So the gradient kind of flows, and then we can train this model end to end. And once trained, the generation is actually trivial. Sample z from normal distribution, and then you can decode it. You'll eventually end up getting some realistic new data because we force the latent space to look like that normal in the first place. Now let's look at this elbow loss, that is this reparameterization trick that we currently see. So what you see in this particular MS, so we said that VA encodes each input as a distribution, right, and wants a smooth latent space. So the actual question is what loss actually makes it happen, and the answer is this elbow. We see it evidence lower bound. So it has two terms, which is this a first term, which is this reconstruction loss, and then this KL regularization loss. Mhm. Uh, and I mean, the intuition is they kind of pull in opposite direction. The first term, which is this reconstruction loss, given a latent code C, how well does the decoder rebuild the original input? This is exactly the same objective a plain autoencoder has. But the second term, that is the scale regularizer, it measures how far the encoder's distribution, that is the skew of Z given X, drifts from prior. So a standard normal Gaussian 0, comma 1 actually. So it penalizes the encoder for wandering off, and that's what forces the latent space to stay smooth, continuous, and well covered actually. So now there's a tension, right? And in the heart of it, the reconstruction wants sharp, confident, and narrow distributions. Basically, it wants uh, to collapse back into a single point so it can copy the input perfectly. So the KL term wants the opposite. It want to spread out, stay close to the prior, and overlap with your neighbors. So the model has to kind of balance these two. And if you put a knob, a beta in front of the KL term, what you essentially get is a beta VAE, where this crank up the crank beta up, and you trade reconstruction sharpness for a cleaner, more disangled input shape. Well, you can interpolate between two latent spaces and get a very coherent transition. This is exactly what this. No, I want to motivate the next. Um, uh, network in this series, that is this VQVAE. Why VQVAE? Where you want to represent images as a grid of tokens. Now the main twist becomes everything so far has used a continuous latent space, right? But if you step back and notice, a lot of uh, the world is actually naturally discrete. If you look at speech, it breaks down into finite number of phonemes, and images again is a collection of discrete things with discrete attributes and an object of some type, same color or same texture. And here is a practical kicker. Our most powerful model, that is this transformers, are actually built to chew on the discrete tokens, not just continuous vectors, right? So the idea here is, what if the encoder that we use turned an image into a grid of vectors, and then we snap each vector to the nearest entry in a fixed code back. Let's say some 512 learned vectors, and each cell in this grid stops being a continuous vector, and it actually becomes a single integer, which is the index of its closest code book. Now, if you use this, suddenly an image is a grid of integers, like a little sentence written in a visual vocabulary. And don't worry that the fixed code is too restrictive. If you can do the arithmetic, let's say a 32 by 32 grid drawing from a 512 word code book can express 512 to the power of 102 for possible distinct images. We have a number which is so large that the model couldn't possibly just memorize. So this is the exact move where you turn an image into tokens, and it is what lets models like DALI generate actually images, and jukebox generate music just by running a transformer over these codes. And this in this particular slide, we'll see what how a VQVAE looks like. The in Where we use discrete latent codes. So let's make that concrete, and how it trains. So the encoder spits out a continuous vector. The vector quantization then snaps each onto this nearest neighbor in this code book, and then that snapped vector is what the decoder receives. But however, there is one obvious problem from a pure ML perspective. The nearest neighbor step that we do, that is this argument, is actually not differentiable. Now there's a hard jump where the when the closest code book vector changes, so the gradient actually naturally can't flow back through it. The workaround is a straight through estimator, and it's actually very blunt. So on the backward pass, we just pretend the quantization isn't there, and then just copy the decoder's gradient straight onto the encoder. But technically, it's a way, but it works actually well in practice. The loss has actually three components. The first, the usual reconstruction loss, where we rebuild the input, and the second is the VQ, or the code book locks, which pulls the chosen codebook vectors towards wherever the encoder is putting its outputs. Third is the what is called as a commitment loss, which exactly does the reverse. It nudges the encoder to actually commit to a code book vector and stop flickering between them, which keeps actually the training stable. Those stop gradient markers in the equation are just bookkeeping. They decide whether each term updates the code book or the encoder, never both at the same time. Mhm. Yeah. And if you want the state-of-the-art image quality, the VQVA2 actually stacks this hierarchically and learns an autoregressive on top of it. So, okay, so far we've been compressing data, right? Now let's use that compression to actually generate things, images, videos, the stuff that everyone is excited about. This is where the dimensional reduction being a mostly a cleanup trick, but becomes a reason modern generative AI is even possible. So here's a quick overview of the generative models, a quick map of the landscape first actually. There are a few big families of generative models and they all try to do the same thing. Learn a data distribution so they can sample new samples from it. Uh, but the way they go about is different. If you look at GANs, they pit two networks against each other. VAEs that we just covered learns a smooth latent space and decodes from it. Flow-based models transform noise into data through reversible maps, and then we have this diffusion, the one where that's taken over image and video generation actually in the last few years. So the idea behind diffusion is almost easy when you first hear it. You take an image and slowly add noise until it's pure static. Then you train a network to undo that one step at a time. So once it can turn back noise into a clean image, you can hand it to fresh random noise, and then it will paint you something new. That's it. The rest of this part is about how to make them practical. Why pixel space is this diffusion is prohibitively expensive? So here's the catch with diffusion, and it's actually a big no big one. So the denoising one isn't one pass actually. The model has to run over and over, sometimes dozens or even hundreds of times to turn noise into single image. Now imagine doing that directly on the pixels. A 512 by 512 color image is around 78,000 numbers, and you're processing all of them like dozens of times for one picture. It gets worse because the attention inside these models scales with the square of the number of positions. So at full resolution, the memory just explodes. So doing a diffusion right on the pixels is painfully expensive. It's the reason why the early diffusion models were slow and capped at small images. And that's the exact moment our earlier lesson actually pays off. We know images now have this low rank structure. Most of the pixels are redundant. So why run this heavy process on all of them? The fix on the next slide is, you know, don't compress first. It is compress first and then do the expensive part in the smaller space. So this is a key idea, and that's what powers the stable diffusion. So instead of running diffusion on the pixels, we run it in the compressed latent space. It's a two-stage setup. Stage one, it trains an encoder, really a VAE that squeezes an image down into a much smaller latent space, and then decode it back with barely any quality loss. Think of shrinking that 512 by 512 image down to some 64 by 64 latent image. Stage two, do all the diffusion repeatedly. uh, and uh, 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 that all repeated adding and removing of noise entirely inside that little latent space. So the flow is encode the image down, do the slow noisy dance in the small space, then decode once at the very end to get your full resolution picture. Because the space is dozens of times smaller, the whole thing gets dramatically cheaper and faster, which is what makes this high quality image generation something you can run on a normal GPU. The VAE from part one is actually doing a heavy lifting there because diffusion just rides on top of it. And these latent here is why this no this matters actually beyond images. If the pixels were expensive, video is ridiculously expensive. Now you have got a stack of frames, so it's height times width times time also. A few seconds of HD video is actually billions of numbers. There's no way you're running diffusion directly on that. So the same trick scales up actually. You build a VAE that compresses across space and time together. So not just each frame, but chunks of frames into a small latent. That's where that's what the Sora does actually. It turns videos into little space time patches in a compressed latent space, and then runs the diffusion there. Google's VUO also takes a similar path. So the one twist is that Sora swaps the usual denoising network for a transformer over those patches, which scales really well uh, as we add compute. But one core enabler is exactly what we've been talking about, the VAE compression actually. Without it, the video generation would cost something like 1,000 times more. So this whole wave of um, sorry for that of generating uh, of generative video really rest on this dimensionality reduction. Uh, let's do a quick check to make it stick. Stable diffusions, VA shrinks by a factor of 8. Um, so a 512 by 512 image becomes a 64 by 64 latent. The question is how much cheaper is the diffusion in terms of spatial size? You can take a guess. So the answer is B, 64 times fewer, not 8, and uh, that's because the factor of 8 applies to both the height and the width. So an 8 by 8, 8 times 8, that is a 64 times fewer positions to process. And since attention cost grows with the square of that, the real C scaling is even bigger. The one number that is this shrinking the thing diffusion runs on by 64x is basically the whole reason latent diffusion is actually practical. So far, the low rank thinking has helped us to compress images and run diffusion cheaply. Now let's point it at the large language models. The same idea that is that the important stuff lives in a smaller number of dimensions turned out to be the key to fine tuning these giant models without uh, a large compute power. This part is basically the low rank tricks applies to the LLMs. So start with the problem the LoRa solves. You got a huge pre-trained model that is just billions of parameters, and you want to fine tune it for your use case or task. The obvious way is to update all the weights, but that really is time consuming because you need a full copy of the optimizer state. You're moving billions of numbers, and every task you fine tune for gives you another full copy of the model, which doesn't scale. So here is a insight behind the LoRa. When you fine tune the changes to the weight, let's call it the delta W, doesn't actually need to be full rank. So in practice, that option actually lies in a tiny subspace. Instead of learning a giant dense update, we can approximate it as the product of two skinny matrices. That's the whole method. You freeze the original weight matrix W, don't touch it, and then you learn a low rank update, a delta W equals B times A, where this A and B are small, very small matrices. Their shared dimension R is tiny compared to the full size. In the forward pass, you just add it on. The output is W times X plus B into A times X. So the frozen model does it thing, and this little BA correction nudges it towards your task. The two important details that are worth calling out, A starts with a small random values and B starts at exactly 0, which means at the very beginning the updates is 0 and you are setting right at the pre-trained model. And once training is done, this since BA is just a matrix, the same shape as W, you can add it straight into the W. We call that merging. So at inference, there's literally no extra computation and no added latency. Uh, and you can fine tune with something like 10,000 times fewer trainable parameters, and each task is just a tiny adapter you can swap in and swap out. That's the reason the LoRa is everywhere actually. Uh, so a quick quiz: why is B initialized to 0? Let's test the initialization detail because it's a great question for understanding. A is random, but B is actually set to 0. Why start B at 0? Uh, Take a second and guess. The answer is B actually. If B is 0, uh, then B times A is 0. So the update delta W is 0 at the start. That means the training begins exactly at the pre-trained model. The adapter adds nothing at first. So you don't disrupt a model that already works. You gently learn towards away from that good starting point. But here is the subtlety that makes it a good understanding. Let's say if you look at option C, why not set now why not set both A and B to 0 is because then you're actually stuck. If both are 0, the gradient to both or 0 and nothing ever moves. The adapter is frozen dead actually. So you need one of these them to be random to break the symmetry and other to 0 to keep the starting update clean. So you randomly initialize A and you start B at 0. That's the recipe. So the LoRa is actually great. People use it everywhere, but people also continue keep improving with. Dora is actually a nice example. The observation behind Dora is that any weight matrix has two aspects. That is how big it is, how that is its magnitude, um, and which way it points. That is its direction. So full fine tuning changes both of those pretty freely and independently. Plain LoRa, kind of lumps them together, and that turns out to limit how closely it can mimic real fine tuning. So Dora, which is this a weight decomposed low rank adaptation, splits the weight matrix into those two explicitly. It writes each weight as a magnitude times direction. It then applies the LoRa style low rank adaptation only to the direction, and then lets the magnitude be its own separately trained parameter. So by decoupling them, Dora gets an extra degree of freedom that the plain LoRa does not have. It can adjust how strongly a weight is separately from where it points, and because that mirrors what full fine tuning does, Dora's learning behavior end up much closer to full fine tuning actually. And empirically, it consistently beats LoRa at the same parameter budget, and it adds only a tiny number of extra parameters. That's just one magnitude value per column. The key takeaway is simple: a smarter parameterization, separating magnitude from direction, squeezes more quality out of the same low rank idea, which is at essentially the same cost. The last one, that is this Q LoRa attacks the bottleneck, a different bottleneck actually, which is this memory. So LoRa cuts the number of trainable parameters, but you still have to hold the full pre-trained model in the GPU while you are actually training. And for really big model, that alone won't fit. So LoRa's move is to quantize the frozen base model down to 4-bit actually. So the weights you are not training take up a quarter of the memory or even less, and then train the LoRa adapters on top of the quantized model. So the base stays frozen and compressed. Only the adapter weights are learned in full precision. The result is that you can fine tune enormous models on a single GPU that previously would not have would have needed a whole cluster. And you can notice the common thread across all these three, right? The LoRa, the Dora, the QLoRa. They all learn on the same fact what we have seen the whole talk, the useful adaptation that it lives in a small low dimension space. You don't need to move billions of parameters to teach a model on a new task. You just need to nudge in a few directions that actually matter. Same low rank principle as the PCA, as the autoencoder bottleneck, as the latent diffusion, just applies, is just applied to this fine tuning also. Right. So in the last stretch, um, so so far we had seen images, the diffusion model, and the fine tuning. Now let's talk about the embeddings, that is the vectors that power search, retrieval, and how a really elegant trick called the Matryoshka represent the learning that lets one model give you many embedding sizes at once. So its dimensionality reduction is baked right into the representation actually. So a quick grounding first. An embedding model takes a piece of text, let's say a word or a sentence in a document, and it turns into a fixed size vector of number that captures its meaning. Similar meanings land close together, and that's what make the semantic search and rank RAG work. So let's say if you have the large models like OpenAI's text embedding three models output some uh, 1500 or so 3000 dimensional vectors. Nomics model is fully open and reproducible 786 dimensions with a long context. And the number to keep in your head is this dimension. Let's say some 786 or some 1500 or 3072. That's the length of every vector the model produces, and as we are about to see, the fixed number actually causes a real headache. So the problem is, once you pick a model, its embedding is fixed in size. A 3070 dimensional model always gives you a 3072 numbers, and there is no cheap way to get a 256 dimensional version without training a whole new model. And that fixed size is expensive. Uh, Storing 100 million documents at 3072 dimension is over a terabyte, often way more than actually what we need for a task. And you might think, fine, I mean, why not just train a smaller model? But what we noticed was the smaller models trained from scratch, they tend to underperform. They never actually got the benefit of bigger training. I know you're maintaining a large number of different size models for different use cases. And if you embed your documents with one size and you query with another, the vectors don't even live in the same space. They're incompatible. What we really want is one model where you can just take the first 256 numbers or the first 512 numbers, and each of those is a perfectly good embedding on its own. That is this nested representations. And that's exactly what the Matryoshka gives us. So the Matryoshka representation learning, named after these Russian nesting dolls, is a simple idea. The question that started it was, what's the right embedding dimension? And the honest answer is it depends actually. So an easy example needs maybe only a few dimensions. A hard one might need many. So why commit to a single size, right? So the MRL's idea is to bake a smaller embeddings uh, inside the full one like this nesting dolls. The first 8 dimensions are valid embeddings. The first 16 dimensions contain those 8 embeddings and more. And the first 32 contain the 16 and so on. And all the way up to the full size. Every prefix is itself a complete usable embedding. So two things that surprise even the others. First, these nested embeddings actually outperform models which are trained independently at each size. You would expect actually a penalty for sharing, but you're getting a bonus. Second, it beats the old approach of running a PC on a big embedding after the fact because MRL learns the structure during training instead of building it afterwards. And you might have heard this OpenAI line, right? Just remove some numbers from the end of the embedding. That's literally this actually. You can truncate to almost any length and it still works, even sizes it was never explicitly trained on. So, how is this? How do you train this? And the answer is very simple. It's actually barely any change. Now you would compute your loss on the full embeddings. Normally, you'd compute your loss on the full embeddings, but with MRL, you compute the same loss at each of these nested sizes. Let's say at 8 dimensional, at 16 dimension, and so on at 2000 dimension, and then just average them together. That's it. No new loss function, no fancy math. But the simple averaging forces something really powerful. Like each doll now has to be a good embedding on its own, or in terms, or its terms in the loss stays high. And because the small dolls are under the more pressure, they show up in the most terms. And the model learns to pack the most important information into the very first dimensions and use later dimensions for the finer detail, like a course to fine automatically. The other neat property is you only train a hand at a handful sizes. That will basically powers of two. But the quality interpolates smoothly to every size in between. So even a dimension uh, you never explicitly trained on still works. One training run, you'll get a whole continuum of embedding sciences. Let's put some numbers on it. On image classification with ResNet 50, MRL at 512 dimension actually beats a dedicated 512 dimensional model. Like let's say some 76% versus 74%. On the text retrieval task, MRL at 256 dimensions keeps about 97% of full 1024 dimensional quality, while an independently trained 256 dimensional model only manages at 92. So the nested version is both smaller and better. And the savings are actually real. Going from like, 3000 to some 256 dimension is like some 12x cut in the storage, and search gets several times faster since it scales with dimension. So the practical sweet spot people land on is around some 256 to 512 dimension that captures the vast majority of the quality for most of the tasks. And anything below 125 is where you finally start to kind of feel the loss. And and this is just a paper. It's also shipping. OpenAI's embedding API has a dimension parameter. When you shorten an embedding there, that's MRL, and it's actually MRL under the hood. Cohere's embed v3 is MRL trained, and they recommend 256 dimension for most of the rack setups and vector databases like uh, Pinecone and VV8 support storing these truncated vectors directly. The killer pattern this unlocks is a two-stage ritual. First, you shortlist, search your millions of documents using this cheap 256 dimensional vectors to grab those top 1000 candidates. Then you re-rank just those 1000 using this 3072 dimensional vectors for precision. And the beautiful part of it is you don't store two separate set of embeddings. The shorter vector is literally the subset or the first chunk of the long one. Best of both the worlds, fast and also accurate. So the big picture shift is that this emerald turns the embedding dimension from a decision you are stuck with at design into a knob where you can just turn at the runtime as per the use case. There's a lot of flexibility for basically for free. So to key takeaways, let me tie the entire whole talk together. Uh, so the PCA gives us a linear dimensionality reduction. The autoencoder made it non-linear. The VAE made the latent space probabilistic and smooth, so we could generate. Latent diffusion ran the whole expansive generation process inside that compressed space, which is why stable diffusion and SOAR are even feasible. And then the Matryoshka gives us nested representation, so one embedding serves every budget. So different names, different papers, but the same core belief runs through all of them. That is this, the high dimensional data really lies in a low dimensional space. And if you find that space, everything gets cheaper, faster, and often better. Whether it's compressing an image, fine tuning a giant model, or serving embeddings at scale. The winning move is the same, reduce the dimensions and keep what matters. That's the final line. Thank you very much. Thank you all.